Okay, students, welcome to video class number 40. And we are in this video, we are starting with a new type of analysis called as the state variable analysis. So far, up to this module 4, we have studied about the transfer function and the application of transfer function to analyze a system, and we have studied a lot about the analysis of a system using transfer function. Okay, so we know how to derive a transfer function of an electrical or a mechanical network, provided the input and the output is given. And similarly, if from a block diagram, you will be able to find out the transfer function. And also using the transfer function, you can have a time domain analysis or time domain specifications, and similarly frequency domain specifications can also be evaluated. And we have studied some graphical as well as mathematical method to analyze a system stability using transfer function. Okay, now so far so good. Now in this video, from this video onwards, we are going to start with we are going to deal with module 5 and 6, and this is module 5. The module 5 is all about the state variable analysis, and that is another type of analysis apart from a transfer function analysis. Now you might be wondering, why do we need another method if you have a transfer function approach? So if you want to know that, you should have an idea about the drawbacks of this transfer function approach. Let's see the drawback of transfer function approach. Number one, the initial condition, it is applicable. The transfer function is defined in such a way that the initial conditions is set to 0. So that is, this transfer function is defined for only for a relaxed system. Now, as far as a practical system is concerned, we know that in a practical system, you have initial conditions, so that has to be considered. So the transfer function will not be accurate if the initial conditions is not considered. In many practical systems which consist of inductance as well as capacitance, there can be always an initial voltage or initial current which has to be considered for the analysis. Now another point is, it is applicable to LTI system or linear time invariant system only. It's limited to single input single output system analysis, and it does not provide any internal information of the system. The internal information of the system will be very feeble in the case of the transfer function approach. And not only that, this transfer function approach is a frequency domain approach, or it's an S domain approach. Now, so these are the drawbacks of the transfer function approach, and thereby the analysis may not be accurate. So in order to have the accurate analysis, especially for a practical system where you will be dealing with the initial conditions, most of the systems you can have initial conditions. So in order to incorporate the initial conditions to its analysis, we have a different set of analysis called as a state space analysis. And one of the major aspect is, this is a time domain approach, or this is a time domain approach. And here in this case, in the state space analysis, you have the option of considering the initial state of the system, and which also will be considered as one of the inputs. Say for example, if you have a network, you have an, say, x of t and y of t. This is the input and this is the output. And now suppose let IC be the initial conditions. There can be more than one initial conditions. So all these initial conditions can be treated as one of the inputs along with this input. So you can consider this as a 4 input system. So each initial condition and this input will be having an impact on y of t. So that can be studied by using state space analysis, and it is applicable to all the systems, be it a linear system or a non-linear system or a time variant system or a time invariant system or a MIMO, or that is multi-input multi-output system. So in that sense, state space analysis is having a greater priority or prominence over this transfer function approach. Okay, now let's see some of the terms associated with the state variable analysis. The number one is state. Okay, state is defined as a group of variables which summarizes the history of the system in order to predict the future value. Okay, this is a layman level of definition. That is, say if you consider a resistive capacitance circuit, a simple circuit like this, you have an input as well as an output for this. Okay, now imagine that this is a charged capacitor, so that charge can yield a voltage across a capacitor initially. So here in this case, this voltage can be a variable which actually determines the history of the system. Okay, so the state the state actually depends on the system which you are analyzing. Okay, so depending on the system, you can have a group of or a set of variables which actually summarizes the history of the system. Okay, for this case, so this voltage across the capacitor gives you the history of the system, so that the output can be predicted. Okay, now if suppose for an RC network, if you consider it as a relaxed system and you perform the analysis, you won't be considering this voltage already present here. That's a problem with the transfer function approach. But in state space, you have a provision of representing this already set value, that is the already set voltage. Okay, so depending on the system, you can have a group of variables similar to the voltage in this case. Okay, it can be a inductive current and so on. I mean, depending on the system you are analyzing, this group of variables can be varied, and this group of variables which summarizes the history of the system is called as a state. Okay, or you will consider each one as a state variable. Okay, so this is just a layman definition, and to be more technical, this is a technical definition. You need to study it by heart. This is the state of system is a minimal set of variables. As in this case, you have the capacitor voltage, minimum set of variables known as the state variables. It is defined as the state variables, such that the knowledge of these variables at t is equal to 0. Okay, at t is equal to 0. And what is the meaning of t is equal to 0? T is equal to 0 is the time at which you give the input. Okay, so the moment at which you give the input, the real input to the system which you are analyzing. So the knowledge at that moment, this set of variables will be having some values, and if you have a knowledge of those variables at t is equal to t0 together with the input, for t greater than t0. Say for example, if you have a system, say this same system, and if you are giving an input u of t, you know the input, right? This u of t is 1 for t greater than or equal to 0. Okay, so here t0 is, in this case you can consider the t0 as 0. It is at the time t is equal to 0 the input is given. Now even before t is equal to 0, this capacitor can be a charged capacitor. So there must be some variable which represents this voltage. Okay, so that variable we call as the state variable. So that's what it says. I'm going to explain it once more. State of a system is a minimal set of variables known as the state variables, such that the knowledge of these variables at t is equal to t0 or t less than t0. Okay, t is equal to t0 along with the input for t greater than or equal to t0 completely determines the behavior of the system. By this knowledge as well as these variables, okay, by using these two factors, you can predict the output at t greater than or equal to t0. So such a set of variables we call as a state variable. Hope you understood the idea about state and state variables. Okay. Okay, now let's move on to another term, which is the state variable. I have already given you an idea about state and state variable right now. The definition is, it is the smallest set of variables used to determine the state of the system. Say, for example, in the above example, we have seen the voltage across a capacitor. Voltage across a capacitor. So there can be initial voltage across the capacitor, right? Then another example is current in an inductor, right? Current in an inductor. So all these can have a can be used as a variables which determines the state of the system, or which determines the history of the system. Okay, so those variables which are used are called as a, or those set are called as a state variables. Okay, now the next term is a state vector. Suppose you have a, say, I have already explained that. Say, if you consider a system, then you can have different sets of set variables, as in the case of this. And say, imagine that the system is an RLC circuit, right? RLC circuit. Then it can have a current in an inductor, voltage across a capacitor. All these can be variables. Okay, so suppose in a system, if you have n state variables, okay, n state variables which are necessary to determine the behavior of the system, then this each state variable can be considered as the n components of a vector. Okay, n components of a vector, and that vector is called as a state vector. Okay, right? So in this example, suppose if you have only two variables, that is a current through the inductor and the voltage across a capacitor, then you have two variables, and these two variables can be considered as a component of a particular vector called as a state vector. Okay. Now, I have already explained that this can be considered as a vector, or all the state variables that you determine or that you are using for the analysis of a system can be considered as the components of a vector called as a state vector. Now, once if you can define a state vector, that can be represented in a space. Okay. Now, if it is a two-dimensional vector, then you can represent that in a two-dimensional space. So that space what we call as a state space. So that means for representing n-dimensional state variables, you can consider those state variables as the elements which can be represented in n-dimensional space called as a state space. Okay. Okay. So keeping all these things which we have discussed, we can again recollect the advantages of the state space analysis. That is, number one is analysis is done by considering the initial state of the system. Okay, so the consequence of this is the system is or the analysis becomes more accurate in comparison to the transfer function approach. Then it can be applied to MIMO systems, linear, non-linear, time variant, time invariant, and all these things. Now, even though this has got more advantages, there can be some disadvantages for this analysis. Now, the following are the disadvantages. One is it's a complex technique. Okay, it's a complex technique anyway. And another point is many mathematical computations are required. Okay, computations are required. Okay, even though these are having the disadvantages, because of the accuracy, many times in critical systems we prefer state space analysis. Okay. Okay, now let's move on to a state model of a dynamic system. Say, consider a system, a control system. Okay, consider a system which has got m inputs. Okay, so this is a MIMO system, right? This is a MIMO system, multi-input, multi-output system. As I told you, the state variable analysis can be performed, and the analysis can be performed on a multi-input, multi-output system. So we are considering M inputs, right? And you have M inputs starting from, I'm calling the inputs as U1 of t, it's a time domain function, U2 of t up to UM of t, Okay, so these side are called as the inputs to the system, the real inputs. Now, similarly, I'm going to define another set of variables, say called as a state variables. Okay, the state variables, and how many state variables? I'm assuming n state variables. So here you have m inputs. So here you have m inputs, right? Here you have m inputs, and you are going to consider n state space variable, and I'm going to represent the state variable as x1 of t, x2 of t, up to xn of t. Okay, do remember I'm using that the designation u for the main inputs, while these are the states. And what do you mean by states? States refers to the history of the system. As in the previous example, as we have seen, it can be in an electrical system, it can be a capacitor voltage or a current through the initial current through the inductor. So for a generalized system, you can have n set of what variables. So these are nothing but, these are the n sets of variables, n sets of, or n what, n state variables. Okay, state variables, right? And which gives you, what is the role of this? This gives the information about what, about the history of the system, or the past, about the past of the system. So even before you give this input, this system gives you the idea about the presence and absence of various voltages or voltage currents, if it is an electrical system present in this. Okay, so even before. So now obviously this, since it is a MIMO system, you can expect more than one output. So let that output be, I'm designating that output to be y1 of t, y2 of t, etc. up to, and here you are considering p outputs. So here you have p outputs, meaning pi yp of t. So this is the outputs, so p outputs. So I'm going to recollect again. You have considered a dynamic system with m inputs starting from u1 to um, and you have a state variable which actually determines the history of the system, similar to current and current of inductor current and capacitor voltage in an electrical system. So you have an n state space state variables, and gives you the information of the past. And so as far this system is considered, these are two sets of inputs given to the system. One is the main input that you give, and the other set is the inherent input that it already have even before you are giving the input. So that is being represented by state variables starting from x1 to xn, and which results in p types of outputs. You can have more than one output, that is y1 of t to yp of t. Okay, now let me again explain. We have already seen state vector and state space and state variable, and I'll be giving you an idea regarding this system again about state variable and state vector and state space. Okay, so in this system, when you let's have a closer look at the state variable. So in this system, you have n state variables, which actually talks about the past of the system. So that means these x1 of t, x2 of t up to xn of t are the state variables. So x1 of t, you can represent that x2 of t up to, you have xn of t, or you can represent this as a matrix, and you can call this as capital X of t. Okay, so this x of t is what is called as the state vector. Okay, this is called as a state vector, and each variable we call as the state variables. Okay, state variables. Okay. Now, in order to represent this x of t in a space, in an n-dimensional space, you can consider this x1 of, you can consider a coordinate system. You can consider a coordinate system with n axis, that is x1 of t axis, x2 of t axis, up to xn of t axis. Okay, right? Similar to x, y, z. So in a three-dimensional space, you will call x, y, z as three axes. So for an n-axis, coordinate system, similarly you can have n coordinate system, and you can represent each in each axis. Okay, and that space we call as the state space, or an n-dimensional. And as far as this system is concerned, this will be having an n-state space. Okay. Okay, so now this y1 up to yp of t can be considered as the p outputs. It is actually the result of, or it is the so this output is obtained by the, or from the knowledge of what? Knowledge of the state variables, as in this case it is x of t. This is a set of state variables at t is equal to t0, or it is the moment at which you give the input. So at t is equal to t0 plus and the knowledge of the input, for t greater than 0. As in this example, it is a knowledge of u1 of t up to un of t for t greater than or equal to 0. So from the knowledge of this state variable and the input, you will be able to get y1 of t to yp of t. Okay, now we are to get the state model. Now model actually refers to a mathematical equation. So a state model, actually consists of two equations. One is called as the state equation, and the other one is called as the output equation. Okay, or in other words, the state equation and the output equation gets combined to give a model called as a state model. So when you have a dynamic system like this, our objective is to get a state equation and the output equation from the knowledge of the inputs given, as well as the state variables present in that system. Okay.